All right, welcome to Let's Get to the Marks. It's AQA Chemistry AS Level Paper 1 2023 walkthrough here. So make sure you hit the like, subscribe to the channel, hit the notification bell so all my walkthroughs come up. Going to be doing them for all the latest papers, and make sure you leave a comment if there's any videos you'd like me to make. All right, question 1. This question is about the elements in period 3. Give the full electronic configuration of the element in period 3 with the highest first ionization energy. So here's the periodic table. Let's go ahead and look at period 3 and work out which one's got the highest ionization energy. Well, sodium has an atomic number of 11 in period 3. Okay, circling it here in blue. Phosphorus, for example, as we go from left to right, has 15. So increased nuclear charge, more protons. That means the electrons are more attracted to the nucleus, especially as we're adding them to the same shell. There's no increase in shielding. This means that argon is going to have the highest first ionization energy. Okay, and it has 18 electrons. So that's all the info we need to go ahead and write out the configuration. So we've got 18 electrons to write out. So the configuration is 1s2. I can put the symbol for argon if I want, Ar. The configuration is 1s2. Then we go to the next quantum level, which is 2. So it's 2s2. And then with each quantum level, there's an extra subshell. So we've got the 2p orbitals, which will be 2p6 because you've got x, y, and z, the 3 different orbitals, each orbital holding 2 electrons. Now we go to the third level. We have 3s2, and then we have 3p6. And that is the electronic configuration of argon, which is the element in period 3 with the highest first ionization energy. So 1.2 says give an equation including state symbols to represent the process that occurs when the second ionization energy of sodium is measured. So one electron's already been removed, which means that sodium is going to be a positive ion in this situation. Okay, now we want to remove another electron. So we just draw an arrow and we go to Na plus, well, 2 plus now, because it's now had the second electron removed. And then we have to show that electron that's just been removed. Now, alternatively, you could write, oh yeah, don't forget gaseous, guys, because we're always in the gaseous state with ionization energy. That will definitely lose you the mark if you don't put G's there. There are other ways to write this. You could write Na plus E minus to show the electron bombarding it goes to Na2 plus 2E, but we don't want to do that. Right, 1.3. Table 1 shows some successive ionization energies for an element in period 3. So we go along in period 3 and it says identify the element in period 3 and explain your answer. Well, there's a huge jump between 6 and 7. Look, jump from 8,490 going over to 27,100. So this means we're looking at the element in period 3 that's in group 6. So we need to go back to our periodic table and check out which element this is. So if we go across here at period 3, where I've coloured it in yellow, and we count 6 elements along to group 6, we'll find that sulfur, that's in group 6, the one with 6 electrons in the outer shell. So there we go. So now it says identify the element, and as we know it's in group 6, because of the big jump between 6 and 7, we can write sulfur, or you can put the symbol S. And the explanation, well, we're going to get a large increase between the 6th and 7th ionization number. Now, what's it a large increase in? You should use the data, the terminology from the table to guarantee the mark. So it's a large increase in ionization energy between the 6th and 7th ionization number. And why is that? Well, because you're breaking into a brand new quantum level or energy shell. So you're removing electrons from the second energy level, or you're removing electrons from a full 2p6 orbital or subshell. Okay, cool. Let's move on. Now going on to question 2. And what have we got here? We've got 2.1. Describe the structure and the bonding in magnesium. So, magnesium's a metal. You've been told in the question here to describe the structure and bonding. So it's really clear there's 2 things you need to comment on. What type of structure does magnesium have? Well, it's got that giant metallic lattice or giant metallic structure. And what type of bonding? It's got metallic bonding. Now at A level, we need to actually describe what is a metallic bond. So it's the electrostatic force of attraction between delocalized electrons and positive metal ions, the magnesium 2 plus ions and the delocalized electrons. And it's a giant metallic lattice, and that'll get you the 2 marks. So one for the structure, giant metallic lattice, and one for the description of a metallic bomb. State the trend in the atomic radius of the elements down group 2 from magnesium to barium. So as we go down any group of metals, group 1, group 2, group 3, the atomic radius increases. And the reason is there are more shells, more quantum energy levels. And what this means is that there is increased shielding between the outer electrons and the nucleus. So although the nuclear charge is increasing, that's outweighed by the increased shielding factor, increased repulsion between those electrons and the outer electrons, and so the atomic radius increases. There we go, 2 more marks. All right, let's move on to the next question. 2.3. Give an equation including state symbols for the reaction of magnesium with steam. State 2 observations for this reaction. So for our equation, magnesium is a solid. We're going to add it to water. Now water is going to be in the gaseous phase because it said steam. So it's pretty obvious that it's going to be a gas. Magnesium, silver metal from group 2. What's it going to form? Magnesium oxide. This is a solid, a white solid or a grey solid. And it's also going to form hydrogen gas. Now, what observations could we make? Well, we're going to see the formation of a white solid or a grey solid. We might see a white light because when magnesium reacts, you get a bright light. And those are your 2 observations. Now, if you haven't already, hit the subscribe button so you become a subscriber to the channel, and also hit the bell notification button. That's the little bell-shaped button there. You can see I've got the icon on there. That's going to allow you to find out when all my latest videos and walkthroughs come up. I'm doing all the 2023 papers, and this year I'm going to try and work through every single AS chemistry paper and A-level chemistry paper that AQA have ever done. Anyway, enough of my waffle. Let's move on. 2.4. The sulfates of the elements in group 2 from magnesium to barium have different solubilities. State the formula of the least soluble of these sulfates. Give a use for this sulfate. So the solubility of the sulfates decreases down the group. So magnesium sulfate is soluble and barium sulfate right down near the bottom is not soluble. Therefore, the formula of barium sulfate, well, Ba has a 2 plus charge and sulfate ions have a 2 minus charge, so it's just going to be a straight BaSO4, and it's a solid. Now, what's the use of barium sulfate? Well, you can use it as a barium meal. Barium sulfate is insoluble and so precipitates and forms an insoluble layer that coats organs, and this means it can absorb X-rays, allowing for medical images to be formed of the digestive system. So pretty good when you're looking for sort of cancers or tumors in the digestive system and things like that. Right, 2.5. A sample of strontium is made up of only 3 isotopes. We've got strontium 86, strontium 87, and strontium 88. This sample contains 83% by mass of strontium 88. The sample of strontium has an AR, a relative atomic mass, of 87.73. Calculate the percentage abundance of each of the other 2 isotopes in this sample, and it's a lovely 4 marks. So we've got the sum of the isotopes. When you do any RAM calculation, you probably remember you take each isotope's mass and you times it by the abundance. So here at GCSE, you'd just be given a straightforward, you'd be given the abundance of each of these isotopes, and you do mass times abundance and then divide by 100 and you get the RAM. Here they've actually given us the RAM, but they've left us without the abundance of 2 of the isotopes and they want us to work that out. So what do we do? Well, we say, well, the sample contains 83% by mass of strontium 88. So therefore we know that one of our calculations that's over the total abundance is going to be 88 times 83. So mass times abundance. And then we have the mass of 86 times whatever it's going to be, and the mass of 87 times whatever the unknown abundance of 87 is. And then you're going to divide all of that by 100, and that would get you the RAM or the AR. And they've given us the AR is 87.73. So we can write that in. Now we just need to figure out what 86 and 87 are. And we can do that by assuming, well, 86 and 87, must be equal to 100% minus 83, right? And that's 17%. We know that the isotope with a mass of 88 is 83%, so that only leaves 17% of strontium isotopes left. And so 86 plus 87 must equal 17, which tells me, for example, um, let's just say 86 is 12%, then that means that 87 must be 17 minus 12, right? 87 must be 5% if 86 is 12%, which means 87 is 17 minus 12. So in that case, we can say 86 is X because we don't actually know what it is, and 87 must be 17 minus X. So now we can fill out up here 86X, and we can write 87 times 17 minus X. So if 86 was 12%, we do 86 times 12 and 87 times 17 minus 12, which would be 5, but it's not those numbers. Anyway, first thing to do here, now that we've decided that 86 is X and 87 is 17 minus X, multiply both sides by 100. This is going to get rid of the divide by 100. And what we're going to have is 88 times 83 plus 86X plus 87 times 17 minus X. And that's going to equal 8,773 because we've times our right side by 100 and the left to get rid of the 100 underneath. And there we go. Now what we want to do is multiply out the brackets. So let's put into our scientific calculator 88 times 83. So you want to calculate that out, and then you want to multiply also out 87 times 17, and then 87 times minus X. So let's put the answers down here into the next part. And you should figure this out to be 7,304 is 88 times 83. Now we've still got that plus 86X plus, now let's multiply out 87 times 17. So we'll do that first. Now this is probably the biggest mistake that people will make in this equation. They will just do 87 times 17 minus X. You need to do them separately. So you do 87 times 17 and you'll get 1,479. And then you need to do 87 times minus X, which gives you minus 87X. And that equals 8,773. So now what we need to do is simplify this. So let's take the 7,304. Well, first of all, we can take the 86X and the minus 87, and that's going to give us minus 1X because it gets rid of 80. If you do 86X minus 87X, you got minus 1X or minus X. Now let's add together 7,304 and 1,479, and that gives us 8,783 minus X equals 8,773. Now we want to leave the minus X on its own. So what we're going to do is subtract 8,783 from each side so that we leave the minus X on its own. So let's get rid of 8,783 from each side. And we're going to be left with minus X equals 8,007. Oh, sorry. Minus X is equal to minus 10. So if minus X equals minus 10, that tells us that X equals 10. Now we know that X equals 10, we know that strontium 86 has an abundance of 10%. As we know that strontium 87 was 17 minus X, we can do 17 minus 10, and that gives us 7%. So strontium 87 must be 7%. And that's because we know that the X is now 10, so we do 17 minus 10 is 7%. And there you go, you get a beautiful 4 marks for this. It's a difficult one. There's quite a few of these and they've come up quite often. So well worth practicing these. I've also got a video on difficult relative atomic mass equations where I go through some other examples of this. So you might want to check the video out here. Let's go. Let's move on. 2.6. Magnesium hydroxide is used as an antacid to treat indigestion. A student does an experiment to determine the percentage of mass of magnesium hydroxide in an indigestion tablet. 40 centimeters of 0.2 mole per decimeter hydrochloric acid an excess, that means the hydrochloric acid is in excess, is added to 0.2 grams of a powdered tablet. The mixture swirled thoroughly. All of the magnesium hydroxide reacts, so we know all of that's reacted with the hydrochloric acid as shown. We can see from the equation it's a 1-to-2 reaction. We'll need that later on, so you always want to write that down when you see these kind of equations. The amount of HCl remaining after the reaction is then determined by titration with sodium hydroxide, where we have 29.25 centimeters of a zero point 0.1 mole per decimeter titration. So now calculate the percentage by mass of magnesium hydroxide in the indigestion tablet. So I'm going to start off by writing the second reaction, which is the excess hydrochloric acid. The leftover hydrochloric acid from the first reaction was then reacted with the sodium hydroxide. And that's a 1-to-1 reaction. You've seen I've written it out there. It's a 1-to-1 reaction. So now let's go back to the top and find the initial moles of hydrochloric acid that we used in this equation, or used in this investigation. So we've got moles over concentration times volume. We know that we had 40 centimeters of hydrochloric acid. So we divide that by 1,000 to get into decimeters. We times by 0.2, which is the concentration, and we get 0.008 moles of hydrochloric acid. Boom. Now it's a 1-to-1 reaction. Sorry, that was the initial moles. That's our starting moles. It wasn't a 1-to-1 reaction. Anyway, how do we know how many moles of hydrochloric acid reacted with magnesium hydroxide? We don't. We just have a load of leftover hydrochloric acid that we then went and reacted with sodium hydroxide. So let's calculate that leftover hydrochloric acid that reacted with the sodium hydroxide. How much was left over? If we can find that out, we can find out how many was used up in the first reaction. So now we do, this is like the back titration bit. So we do 29.25. We divide it by 1,000. We times it by 0.1. These are our moles of sodium hydroxide, and we get 0.00295 moles of sodium hydroxide were titrated. Now we know it reacts in a 1-to-1 with HCl, so that means that there must have been 0.00295 moles of HCl left over after that initial reaction when it was in excess. So let's now work out how many moles actually reacted. So how many moles of HCl were used up? We had a total of 0.008. We know that 0.00295 was left over because that's what reacted with the sodium hydroxide. So let's find out how much originally reacted with the magnesium hydroxide. Well, what we're going to do is we're going to take the initial moles, 0.008 moles, and we're going to subtract the excess moles of hydrochloric acid that reacted in the titration. So we're going to get an answer here of 0.00505 moles of hydrochloric acid reacted with the magnesium hydroxide. Now check out the ratio. It was a 2-to-1 reaction. So how much magnesium hydroxide was there? Remember, that was all fully reacted, and we highlighted that. That was part of the stem of the question. So how many moles of magnesium hydroxide were all used up and reacted in that first reaction? Well, we need to take the moles of HCl, which was 0.00505, as it was a ratio of 2-to-1. We need to divide it by 2 to find how many moles of magnesium hydroxide we originally had in the tablet. You can see here I've highlighted in pink, there's the ratio of 2-to-1 of acid to magnesium hydroxide. So we're going to go 0.00505 divided by 2. We're going to find out that we had 0.002525 moles of magnesium hydroxide. So now we know our moles of magnesium hydroxide. We now need to find the mass of magnesium hydroxide so we can work out the percentage of it in the 0.2 gram powder tablet. So I'm running out of space, so I'm just going to come up here and write your moles mass equation. So that is mass over the MR times moles. So I want to find out the mass, so I'm going to do 0.002525. That's the moles of magnesium hydroxide, and I'm going to times it by the MR. So do 24.1, or just 24 for magnesium, and then add it to oxygen and hydrogen, which is times by 2. So 17 times 2, and then add that to 24. And then you've got your MR, which is 58. If you want to be precise, 58.1, but you don't need to be that precise. So 58.1 times the moles, we're going to find we have 0.146 grams of magnesium hydroxide. Now, does it make sense? Yes. If it came out bigger than the powdered tablet, you know you've made a mistake, but it's less than the powdered tablet. Obviously, it can't weigh more than the tablet itself. It's part of a mixture which only weighs 0.2. So now we do 0.46 divided by 0.2, and we times it by 100, and we get the percentage of that tablet that was magnesium hydroxide. I know it's a lot of work for these marks, but you'll find that I have got a few videos on the amount of substance. And if you want to try them at some point, I'll put a link to them in the description. And it's 73% your answer here, and that will smash you out to 4 marks. Awesome. Right, let's move on. Right, we're on to a whole new question. Question 3. A student uses this method to prepare a standard solution of sodium carbonate. Weigh a clean, dry, empty container on a balance that reads to 2 decimal places. Add about 2.5 grams of solid sodium carbonate to the container. Tip the solid into a beaker. Add approximately 100 centimeter cubed of distilled water to the beaker and stir until all the solid is dissolved. Pour the solution into a 250 centimeter cubed volumetric flask. Add distilled water until the top of the meniscus is level with the graduation mark. Suggest 3 improvements. Right, bust out the highlighter here and highlight some of these key points and try to spot where they could have made some improvements in this method. Yeah, use this type of highlighter, not the other one. Okay, yeah, so you should be able to see some mistakes in the method. So let's suggest 3 improvements to the method. First of all, look at the way they weighed it. They weighed out 2.5 grams and then they tipped it into the beaker. Now, with all of the 2.5 grams of sodium carbonate left the container, you're going to have a tiny, tiny amount, whether it's 0.01 grams, you're going to have a tiny amount left in the walls of the container. So what you really should do is reweigh the container after emptying the solid, compared to the original weight of the empty container, and then you'll know how much of the 2.5 grams was actually tipped into the beaker. Far more accurate way of doing it. Also, put all your washings into the volumetric flask. So when you stir with a glass rod, that also may have some solid or some solution on it. So with the dissolved solid in it. So we need to wash that with distilled water into the volumetric flask. That's called your washings, and you need to rinse that all into the volumetric flask. Another thing, put a stopper in the top of the volumetric flask and turn it upside down. You can say invert the flask several times to ensure everything is thoroughly mixed. And there we go. That's going to get you all the marks you need to smash through these 3 marks. All right, guys, we're going to move on to the next question. Keep moving on, keep moving on, keep moving on, keep moving on. All right, guys, make sure you hit the like. It helps these get bumped up in the algorithm. Whatever that is. 3.2. A different student uses the correct method to prepare 250 centimeter cubes of sodium carbonate solution in a volumetric flask. The uncertainty of the volumetric flask is plus minus 0.2 centimeter cubed. Calculate the percentage uncertainty. So we're just going to do the uncertainty of our flask, of our apparatus, divided by the measurement we made times 100. It's unlike biology where you often get 2 marks and you've actually got to calculate the uncertainty first before you do the percentage uncertainty. Here they've given us the uncertainty as 0.2, so we take them at their word. Here we go. Let's go. Okay, another amount of substance. We've got M as a group 2 metal that forms a nitrate, MnO3 The NO3 is in brackets with a 2 outside. 0.320 grams of N nitrate, metal nitrate, is heated strongly and decomposes completely. The mixture of gases formed has a volume of 225 centimeter cubed at 450 degrees and 101,000 pascals. Determine the MR of M from the metal nitrate. Identify M. Well, we know because we've been given R is 8.31, we need to use PV equals nRT. We're looking to find the MR, so we need N so that it can go in our MR and mass equation. So we're going to do PV over RT equals N. We know the pressure is 101,000. They've given that to us nicely in pascals. We've been given the volume, but you must convert to meters cubed in these ideal gas equations. You can do that 2 ways. You can do 225 times 1 times 10 to the minus 6, or you can divide by 1 times 10 to the 6, both the same. Now that's going to be divided by 8.31, the gas constant, times 450 degrees, but turn it into Kelvin for this, so add 273. Now you've done that, you'll have scored for the rearrangement, you'll have got a mark. For the correct conversions, you'll have got a mark. You'll be on at least 2 marks here. Now we're going to get 3.78 times 10 to the minus 3 moles, but remember that's of our gas mixture, okay? Now we need to use the ratio from the equation. Now, if we look at the ratio in the equation, we've got 4 nitrate gas molecules and 1 oxygen gas molecule. That's a total of 5 moles. So that's a ratio of 5 moles of gas to 2 moles of the metal nitrate. So what we're going to do is we're going to times 3.78 times 10 to the minus 3 by 2 divided by 5, right? And that is going to give us the amount of moles of metal nitrate. Now, if you don't really understand that, you could say, right, let me work out the moles of oxygen. And you could say, I'm going to divide 3.78 times 10 to the minus 3 by 5 to find out how much 1 oxygen mole is. And then I'm going to times it by 2 because it's in a 1 to 2 ratio with the metal nitrate. So you could do it that way as well. Now that we know our moles of the metal nitrate is 0.001512, what we can do is stick it in the mass over ml times moles. So we're going to have 0.320 grams over the top of 0.001512 mole. So what we've calculated here is that the MR of MnO32 is 211.6 is the MR. So if we want to find M, we need to subtract NO32, which is 14 plus 48 times 2. We need to subtract that, which is total 124, from the 211.6, which is the full formula's MR. And if we do that, we'll find out the MR of the metal M. And then we just need to look it up in the periodic table and identify the metal. And so we can see with an MR of 87.6, if we look here in group 2 of the periodic table, you'll find strontium is your unidentified metal. So there we go. Boom. Now let's move on and clear this screen of all the rubbish. Move on to the next question. Okay, this question is about shapes and molecules. Discuss the difference between the shapes of CF4 and XeF4. In your answer, you should name the shape of each molecule, explain the shape of each molecule, explain the bond angle in each molecule. So really clear that you're going to get really a mark for each of those, and you need to do 2 names of shape, 2 explanations, and 2 correct bond angles to get all 6 marks. So let's start with CF4. Well, the central atom, I'm going to go into a little bit more detail. The central atom has 4 electrons around it. I use E minus as my shorthand for electrons. Now it gets another 4 electrons around that central carbon atom donated from the fluorine, and we can tell that by the number of bonds because it's got 4 bonds because of F4. So there's a total of 8 electrons around the central carbon atom. Divide that by 2 and you'll find the number of pairs of electrons around that central carbon atom. So there's 4 pairs of electrons around the central carbon atom. 4 from the carbon, 4 from the bonds. Or 4 from the fluorine, sorry. This means you're going to have to be, if you have 4 pairs, you're either going to be tetrahedral, pyramidal, or bent nonlinear. Which one are we? Well, there's no lone pairs, and we can tell that because there are 4 pairs of electrons, and we know all 4 pairs of electrons are in a covalent bond with fluorine because of the F4. So no lone pairs. Now, that means it's only bonded pairs around the central carbon atom. So the shape will be tetrahedral, and that's going to get you your first mark. Okay, you don't actually have to draw the shape out. It doesn't ask for that. It just says name the shape, but I'm just going to draw it out for you there. That's what a tetrahedral shape roughly looks like. Now, we've got bonded pair repulsion, which means that the electron pairs try to get as far away as possible from each other as they can. And in this situation, the furthest they can get away from each other is a 109.5 degree bond angle. So we've also got the mark here for the bond angle and for the explanation of the repulsion between the bonded pairs. It's a symmetrical molecule, so the repulsion is even everywhere, which is why there's a 109.5 bond angle. And that's going to get you your 3 marks for talking about CF4. Now I'm going to do the other in another color. Let's look at XeF4. So we've got xenon here as the central atom. There are 8 electrons around it, plus it's getting those 4 electrons donated from the fluorine atoms. So there's a total of 12 electrons. Divide that by 2 and we'll find we have 6 pairs of electrons around the central atom. Now we know that 4 of those 6 pairs are bonded pairs because we've got the fluorine, the F4, that tells you the number of bonded pairs. So 6 minus 4, there are 2 lone pairs. Now, the way that these position themselves, there are two different bond angles going on here, and that's because um, we've got the bond between the fluorine atoms and the lone pair, and then we've got the repulsion between the two lone pairs. Now, the shape is square planar, so that's going to get you a mark. We do need to know that the bond angle of the XEF bonds, the bonds between the fluorine and the xenon, are 90 degrees, and these are symmetrical. So 360, they're all in the same plane, which is a 360-degree plane. Divided by 4, they're 90 degrees each. They get as far apart as possible. However, there's greater repulsion between the two lone pairs. So each lone pair is 180 degrees apart from each other. Don't forget, A levels can be very, very difficult, and at times they can leave you feeling a little bit stressed out.
I can't handle the stress no more, dog. These damn A levels.
Now, there's no need to get stressed because I'm going to be doing plenty of walkthroughs on tons and tons of packs of questions. Check out my physics and maths tutor style walkthroughs where I go through question packs from their websites. All right, let's go through and check out the next question. Question 6. This question is about halogens and halide ions. Explain why the electronegativity of the halogens decreases down the group, and it's worth 2 marks. So as you go down the group with the halogens, you've got to think what happens to the size of those halogen atoms as we go down the group. Well, they get bigger. And this means the outer electron is further from the nucleus, or the electron that is to be attracted, I should say, is further from the nucleus, further from that nuclear charge, and is more shielded. So you take fluorine, which is the most electronegative element. It's very small, it doesn't have a lot of shielding, and it has quite a high nuclear charge. So therefore, the electron is strongly attracted to the fluorine atom, which is why it's the most electronegative. Okay, concentrated sulfuric acid reacts with solid sodium chloride and with solid sodium bromide. So two similar reactions. State a similarity in the reaction and one difference. So here I've got the sulfuric acid plus sodium chloride, and it goes to hydrochloric, or hydrogen chloride, I should say, plus sodium hydrogen sulfate. You can write this as sodium sulfate. It's a little bit harder to balance. And if we look at the reaction with sodium bromide, look, they both form hydrogen halides. The difference is that because bromide ions are a stronger reducing agent, they can go on to actually reduce the sulfuric acid because it's in excess, the sulfuric acid, they can go on and reduce that to form bromine and sulfur dioxide. And the difference here is that in this second reaction of the bromide ions, they reduce the sulfur atoms from +6 oxidation state to a +4 oxidation state. So the sulfur atoms have gained 2 electrons and been reduced. So bromide ions will do a redox reaction. The chloride ions are not a good enough reducing agent to reduce the sulfur. If you look at the sulfur atoms in sodium hydrogen sulfate and in sulfuric acid, they haven't been reduced. Okay, solid sodium iodide, which is even stronger a reducing agent, iodide ions, reacts with concentrated sulfuric acid to form hydrogen sulfide. Give a half equation to show the oxidation of iodide ions. Give a half equation to show the reduction of concentrated sulfuric acid to hydrogen sulfide. Use your half equations to deduce an overall equation for this reaction. Again, I've used a highlight array. Can't recommend it strongly enough when you're actually doing real exam papers. It's a key technique in you not losing easy marks. Okay, half equation. We've got 2 iodide ions. They're going to come together to form covalently bond to form iodine and chuck away those 2 extra electrons. So that's your half equation. Now what we're going to look at, why is it oxidation? You know, oil rig, oxidation is loss of electrons. The iodine is losing electrons. That's why it's oxidation. Now we're going to look at the second half equation. So we're looking at the reduction of sulfuric acid to hydrogen sulfide. So start on the left with sulfuric acid, write your hydrogen sulfide on the right, and now look at those 4 oxygen atoms on the left. That means we have to add water to balance that up. How many waters do we need to add? We've got 4 oxygen atoms, so we need to add 4 water molecules. This poses a problem because now I've got an extra 8 hydrogen atoms on the right. What we can do is go back to the left and add hydrogen ions to balance that up. So we've now got 10H on both sides, which is cool. One of the problems is there's no electric charge on the right. Hydrogen sulfide and water are neutral, but I've now got 8 positives on the left. So I have to add in 8 electrons to make it neutrally charged on either side. And there we go. Those are the two half equations. Now we're going to write the overall equation. The key when you have two half equations is to balance the electrons. So what you're going to do, the top half equation only has 2 electrons. So we're going to put times 4, times everything by 4 there, and then you just write it all down to the overall equation. So you go, right, I'm going to have, on the reactant side, I'm going to have 8 iodide ions, plus 1 molecule of sulfuric acid, plus 8 hydrogen ions. Then we're going to go plus 8 electrons. If we want to write in the electrons at first, we can. We are going to get rid of these later, and I'll show you why. And then on the right-hand side, we have 4 iodine molecules. Remember, we times it by 4, everything in that first half equation. So we've got 4 iodine molecules. And that balances neatly with the 8 iodide ions on the left-hand side. Now we need to write 8 electrons, because I put 8 electrons on the left. You don't normally include the electrons. I'm just writing them here to show you it's like the working out. We will get rid of those. And then I've got a hydrogen sulfide molecule and 4 water molecules going off the page, as you can see. Now we should really just cross out those electrons, get rid of those, just give myself extra work, and now patch all of this up. We don't need those electrons. Why don't we need the electrons? Oh my gosh, what is going on? Yeah, we don't need those electrons. So let me just drag this all over because they cancel out on either side. There we go. And notice the charges are neutral. You know you've done it right if all your electric charges are balanced on either side. And we've got 8 minus and 8 plus on the left, which is no charge, and we've got no charge on the right, so it's perfect. All right, always check those things when you're doing half equations and overall equations. Are they balanced in the number of atoms, but are they also balanced in the electric charge? Right, question 7. This question is about time of flight mass spectrometry. Okay, compound X is dissolved in a polar volatile solvent and is ionized by electrospray ionization. Use that highlighter to identify those key points. Each ion is accelerated so that it has a kinetic energy of 1.36 times 10 to the minus 16 joules. We're going to use the equation Ke equals half mv squared. We got kinetic energy. Just remember that mass is in kilograms in this. Time of flight along a 0.750 meter tube is 2.48 times 10 to the minus, what the hell is that? 5 seconds. So what we're going to do, determine the mass in grams of 1 mole of X. So zooming out here, the first thing I want to do is do V equals D over T. We've got the distance 0.750 and we've got the time 2.48 times 10 to the minus 5 seconds. That gives us the velocity of 30,241.9 meters a second. Now we're going to take that second equation, kinetic energy equals half mv squared. So what we want to do is first of all get rid of the half. Most people do this by timesing by 2. So therefore you end up with 2 times the kinetic energy over the top of v squared, because we need to divide both sides by v squared. So let's carry out that and find out what our mass is. So 2 times 1.36 times 10 to the minus 16, that's the joules. We're going to divide that by the velocity that we calculated at first, which is 30,241.9 meters a second. We're going to square that answer, and that's going to give us 2.97 times 10 to the minus 25. Now that's kilograms, but remember that our answer, I've circled it in black there, wants it in grams. So I need to times that by 1,000 to get 2.97 times 10 to the minus 21 grams. However, that is just for one ion. Remember, this information was about an ion, and the question says, determine the mass of a mole. So I now need to times this by 1,000 to get the mass. Times it by L, which is Avogadro's constant, to get the mass in moles, because there'll be 6.022 times 10 to the 23 ions in 1 mole. So times it by that and we get 179. So that tells me that we should have 179 grams of this compound X in 1 mole. However, the final step, remember we highlighted at the start, is to -1. How did we know to do that? We used electrospray ionization, which is where a proton is added to create a positive charge, so it's attracted to the negative detector plate. And in this version of time of flight ionization, you have to add a proton. So we're going to subtract 1 to get the correct answer. There we go. Right, 7.2. A mixture of gases is analysed using time-of-flight mass spectrometry. The mixture contains argon, carbon dioxide, nitrogen, oxygen. The mixture is ionised by electron impact. This is a different type of ionisation. State the meaning of the term electron impact ionisation. This is where a beam or ray of electrons strike a compound and remove electrons from its atoms, therefore creating a positive ion. In this one, the MR, or the mass, has not been increased. It's just lost an electron. If anything, the mass has gone down ever so slightly. Identify the ion formed from this mixture that reaches the detector last. Right, which is the heaviest? You just got to work out the mass number. Carbon dioxide's got a mass of 44. So the ion of carbon dioxide that will reach the detector last will be CO2 plus. 44 is bigger than the mass number of all the other elements there. It's got the largest mass, so it's traveling at the lowest velocity. Students often get confused and think, don't they all travel at the same velocity? No, they have the same kinetic energy, but as they have different masses, they travel at different velocities. 7.4, state how the ions are detected and how the abundance of each ion is measured in the TOF mass spectrometer. So the ions are detected at what we call the negative plate. It's a negatively charged detector plate. As the ion approaches the plate, a stream of electrons, a stream of negative charge, a current, will move from the negative detector plate into the positive ion. Now, the size of the current, how many electrons are flowing into the ions, is directly proportional to the abundance of the ion. So if I have 50 carbon dioxide ions, I'm going to get 50 electrons moving over, and that will read on an ammeter a certain amount of current. Okay, so the current is proportional. Lovely. And this is my crusty drawing to show that. Yeah. So if I've got 2 carbon dioxides, I'm going to get 2 electrons zipping out to there. If I have 3 carbon dioxides, I'm going to get 3 electrons zipping out from the negative plate. So you can see it's proportional. The higher the abundance of the positive ions that reach the detective plate or detector plate, the higher the current. Let's move on. What's this? Question 8. About time. The question is about the equilibrium mixture formed when A and B react. We've got A plus 2B goes to C, reversible. It's exothermic with a minus 32 kilojoule per mole. So again, you should be busting out a highlighter to identify all these key facts. Now, a solution containing 0.6 moles of A is added to a solution containing 0.6 moles of B. The amount of C formed at equilibrium is 0.28 moles. Deduce the amounts in moles of A and B in the mixture at equilibrium. Now, there's different ways to do this. One of the ways that is popular among people is to draw a kind of like little table and you write ICE down the side. It stands for initial, change, and equilibrium. So what are the initial moles of A, B, and C at the very start of the reaction when it has just started? Now, and then afterwards, what are going to be our moles at equilibrium? And we want to put a little change there as well. Oh, I need to get rid of that disgusting line. There we go. Right, so our initial moles of A at before equilibrium, when they're first reacted, is 0.6. Our initial moles of B at the start of the reaction will also be 0.6, right? Because we've just started the reaction. What about C, the product? Well, it has to be 0 at the start of the reaction because the reaction hasn't taken place yet. Now, how much does it change by? Well, we know C changes by 0.28 because we've been told there's 0.28 moles at equilibrium. So it added 0.28. What we do now is look how much the others have changed. And to do that, you times them by the ratio in the balanced equation. So The ratio of B to C is 2 to 1. So we've got a times, you get double the change in the moles of B than you do of C. So you go 0.28 times 2, and you're going to get 0.56 for B as the change. Whereas with A, it's a 1-to-1 ratio with C. So you're also going to get a 0.28 change. And if you take 0.28 from 0.6, you get 0.32. Cool. So B changes by 0.56. So how much does that leave you at the end at equilibrium? If it's changed by 0.56, it's going to leave you with 0.04. And so our answer, we have 0.32 moles of A and 0.04 moles of B. And that's going to get you the 2 marks. So you can use that ICE method. Now, moving on, 8.2, give an expression for the equilibrium constant for this reaction. So this basically just wants you to give an algebraic expression. Don't go writing any numbers in when it asks for an expression. We don't need to do that. So we just want to do products divided by reactants, looking at the equation that we had above. And so what we should have is Kc is going to be equal to C, which was our product, over A times B, our reactants. Don't forget to put a little 2 outside the brackets for the B, because there were 2 moles in the ratio. Now, we use square brackets because that represents concentration. Don't round the brackets. If you round them, that will be pressure and you won't get the mark. Right, 8.3. The temperature of the equilibrium mixture is decreased. Predict the effect, if any, on the value of Kc and give a reason for your prediction. So if we decrease the temperature, what would happen to the Kc? And this is why they asked us to write the expression. We can now work it out. So when you're changing the temperature of a reversible reaction, you need to find out, is the reaction exo or endothermic? Otherwise, you won't know what happens. So we've been given the -32 symbol. That tells us it's exothermic because it's a negative energy change, right? Energy is released. So we've now got to use Le Chatelier's principle in our head and say, right, if you decrease the temperature, Le Chatelier says the reaction will move to counter the change. So the reaction is going to shift to the right, because if you decrease the temperature of an exothermic reaction, the reaction favors the right-hand side to counter the change. That's Le Chatelier's principle. So we know it's going to shift to the right and make more product. So we're going to get an increase in C. Think back to the Kc equation. If you expression we did in the previous question, if you get a larger C and it's products over reactants, what is that going to give you? Give to the value, do to the value of Kc. So you can think, well, what is 5 divided by 2? Well, it's 2.5. Let's make the top number, which would be C, bigger. What's 10 divided by 2? Oh, it's 5. So the Kc has increased. So we know that the Kc will increase in this situation. Okay, let's look at 8.4. In another mixture, so they're telling us we're not using the same data. A is 0.48 mole per decimeter concentration, and C is 0.62. For this reaction, the Kc is 7.8 mole to the 2 dm6. What we want to do, mole to the -2 dm6, calculate B at equilibrium, give your answer in the appropriate number of significant figures. Now, they've given us the units, which is very kind of them, so we don't have to work out the units. Okay, so we've got 7.8 for Kc. We just need to remember that that was equal to, Kc was equal to C over A times B squared. So we want to get B squared on its own. So we're going to do 0.62 over 0.48, which is A, times our unknown B squared. Now we can rearrange this so that we're going to do 0.62 over 7.8 times 0.48, and that is going to be equal to B squared. However, we want to get rid of the B squared because we just want to find B. So we square root both sides. And so we have the square root of 0.6 divided by 78 times 0.48. Now you want to do those in brackets, each of those, so that you get the correct answer. If you don't use the brackets in your scientific calculator, as I mistakenly do quite a lot of the time, you're going to get the wrong answer and you're going to lose. Yeah, so the answer is 0.4069. And it did say to the appropriate number of significant figures, so we're going to round that up to 0.41, and that's to 2 sig. So lovely jubbly. Right, we're going to move on to the next question. And it's the multiple choice, guys. So question 9, which atom contains the most neutrons? Well, if you use your periodic table, you'll find out that all of these have 30 neutrons except for iron, which has 31 in this situation. Just subtract the mass number from the proton number. You'll find the atomic or proton number in the periodic table for each of these. Right, next question. Use this information to answer questions 10 and 11. A student completes a titration to determine the concentration of ethanoic acid in vinegar. 25 centimeters of vinegar are transferred to a conical flask using a pipette. A few drops of phenolphthalein are added to the conical flask. Sodium hydroxide solution is added to the burette. And then is titrated to the conical flask. The titration is repeated until concordant results are obtained. What improves the accuracy of the titers? If we rinse the conical flask with vinegar in between titrations, that's not good because we'll be adding moles of vinegar and that's going to mess up our experiment. Rinsing the conical flask with sodium hydroxide would be done because that's what's going in the burette. So that's going to cause all sorts of problems. Rinsing the conical flask with water between each titration, yeah, that's good. You might say, hold on a minute, doesn't that dilute the concentration of what's in the conical flask? We're not bothered about that. We're just bothered about the moles that will be transferred there via a pipette. That will not change by you having a few water drops in the conical flask. Okay, question 11. Which suggestion decreases the percentage uncertainty in the mean titer? So if we use a more dilute solution of sodium hydroxide in the burette, if we use a more dilute solution of vinegar in the conical flask, rinse the inside of the conical flask with distilled water, no. Rinse the tip of the burette, no. What you want to do here is create a larger volume. That's always going to decrease the percentage uncertainty. And so we want a larger titra. And in order to do that, what's going to take longer for neutralization to occur, that's going to be by diluting the sodium hydroxide in the burette. Means we're going to have to add more to neutralize the vinegar. So we're going to decrease the percentage uncertainty. Aha, you might say. How come using a dilute solution of vinegar doesn't decrease the percentage uncertainty? But remember that if you dilute the vinegar, you've not changed the amount of moles in there, so you're not going to change the size of the titra, the amount of sodium hydroxide required to neutralize it. All right, let's move on. Which reaction has the highest percentage atom economy? This is question 12. For the production of hydrogen, what you want to do is just do the useful product over the total products. So here you're going to do H2 over LiOH plus H2. So you're going to do like 2 over 26. Bash that into the calculator and see which is the highest number. So 2 divided by 26 gives us 0.076. Then the next one is 2 over 46. And then like obviously 6 for this next one because there's 3 lots of hydrogen, 6 over the total. And then here we got like 6 divided by 34. And so, yeah, I think it is going to be either A or D. Let's have a little look. It's going to be D. Yeah, because see, D is going to be a bigger fraction. So if I do 6, which is 3 times H2, divided by CO plus 3 times H2, so it's going to end up being 6 over 34 when you add up all those MRs. That's going to give me a higher atom economy. Obviously, you should do this then times 100, but I'm just doing the quick hand way. Okay, so that one has the largest atom economy. And if you want to find out the percentage atom economy, you just press equals on your calculator and times 100. Right, which molecule has a permanent dipole? Is it NCl3, CCl4, PF5, or SF6? Well, the fact that the nitrogen atom has a lone pair means that there is a permanent dipole on this molecule. So there we go. Easy peasy. Question 14. Which molecule can accept an electron pair during the formation of a coordinate bond? So a common answer that would be a mistake here would be to go for the ammonia molecule because ammonia loves to get involved in dative covalent or coordinate bonds. And the reason is the ammonia can donate a pair of electrons, just like the NCl3 above. The NH3, the ammonia, has a lone pair of electrons, and look, it can donate these electrons to something else, like especially when it forms ammonium, the ammonium ion. However, that's not what the question's asking us. The question is saying which of these could accept a pair of electrons into its outer ring, and the answer is aluminium. Aluminium in group 3, only bonded to 3 chlorine atoms. It has room to accept extra electrons into some of its orbitals. And so that's the answer there. Now for this next question, what we're looking at, 15, which reaction has an enthalpy change equal to the standard enthalpy of formation of potassium oxide? They're basically asking you which of these is the standard enthalpy formation of potassium oxide, which one is correct. And if you know your definition, it's got to be in standard states and it's got to be 1 mole. So we can get rid of ones that form 2 moles. So get rid of A because it forms 2 moles. So that's not a standard enthalpy of formation. And then we want them in their standard and correct states. Now you can see B has a bit of a problem. Oxygen doesn't come like that. It's diatomic. It should be O2. So D is the correct answer because they're in their standard state. C, they're ions, and they're not going to be operating as ions in their standard state. 16, in which species is chlorine in the highest oxidation state? So what we need to do here is they're testing you on can you work out the oxidation state. So fluorine is the most electronegative element. It's always -1. So you've got 2 times -1 is -2. There's an overall charge of minus, so the chlorine has a +1 charge. For B, we've got oxygen, which is 2 minus. So we've got a total of 8 minus. 4 times 2 minus is 8 minus. There's an overall minus charge, so the chlorine must be +7 to give that -1 charge overall. ClO2, yeah, we got a -4 electric charge, so chlorine is +4, and ClF3, as we said before, fluorine is always -1, so we've got a -3 from the 3 fluorine ions, so chlorine is +3. So the answer is B. That is where the chlorine has the highest oxidation state. Right, 17, which statement about this redox reaction is correct? So let's check out the first one. We've got tin here, a tin ion. Sn2 plus is the oxidizing agent. It gains electrons. Well, oxidizing agents, they cause things to be, oxidizing agents themselves are reduced. But let's just check out what tin does here. Does it act as an oxidizing agent? Well, actually, it's losing electrons here. So it's not acting as an oxidizing agent at all. It's actually acting as a reducing agent, the tin. And this second one says, well, the tin is a reducing agent. That statement's correct, but then it says it gains electrons. Well, we just proved that's wrong. Let's look at the chromate ions, the dichromate ions. Is a dichromate an ion an oxidizing agent or a reducing agent? Well, it goes from +6 to +3, which means it is gaining electrons. Both of those could be the correct answer. But if you gain electrons, you're being reduced. You're acting as an oxidizing agent. So the answer is C. Things that gain electrons are being themselves reduced, and therefore they act as oxidizing agents because they cause something else to lose electrons because they steal the electrons off of them. Right, 17, 18. Da-da-da-da. Which incomplete half equation is balanced by adding 2 hydrogen ions and 1 electron to the left-hand side? This one's quite easy because there's only one here with electric charges. So you're not going to be able to balance anything by adding 2 plus and 1 minus to the left-hand side. So if we look here, the first one, if you add 2 hydrogen ions, this is not going to improve the balancing by adding an electron. You're changing the electric charges of either side of the equation. Whereas here, by adding 2 hydrogen ions, you make it +4, but then you add an E minus, which makes it +3. And so it's +3 and +3 on both sides. So that one is correct. You look at the other two, they're both neutral equations as they stand. Changing the electric charges on one side is certainly not going to balance something. And for the final few questions, we need to use this table and study it to work out the answers. A student completes some test tube reactions on 5 solutions, P, Q, R, S, and T. The student completes each test on separate samples of each solution. Their observations are shown in the table. So we've got 5 solutions, P, Q, R, S, and T, and you can see first of all, they've added some sulfuric acid and checked for any changes. Then they've done nitric acid and silver nitrate. Then they've done a few drops of sodium hydroxide, and then they've kind of tried to do some sort of halogen displacement reaction using chlorine. So let's have a look at each question and then go back to the table and see if we can solve it. 19. Which solution contains carbonate ions, PQR or S? So what we want to do is scroll back to the table and say, right, let's do the acid test. If they had a carbonate, what would happen if you added acid to carbonate? You get bubbles. What's another word for bubbles? Effervescence. So we can see here that Q must contain a carbonate because it gave off a gas. And when you add an acid to a carbonate, you're going to get bubbles, and that's the carbon dioxide being released from the carbonate. Awesome. So that's 19 done. Now we need to move on to question 20. Again, we're going to keep having to scroll back to actually see and look at the table and work out the answers. So question 20. What could be the identity of the compound in solution P? Is it magnesium bromide, barium bromide, magnesium chloride, or barium chloride? So we want to find out the identity of the compound in solution P. So it's one of these. So really we're looking, is it magnesium or barium, the metal ion? And then is the anion bromide or chloride? So let's have a little look. They've added hydrosulfuric acid. Okay, we've got two that form white precipitates with sulfate ions. Now, P forms a white precipitate. So does S, actually. The barium ions, they will join with sulfate ions in the sulfuric acid to form barium sulfate. And you should know from your group 2 knowledge, barium sulfate is insoluble white precipitate. So this is a positive result that there is barium involved. Now they've added nitric acid and they've added silver nitrate and got a cream precipitate. Okay, so do you remember your halide ion tests? If you add silver ions to bromide ions, you get silver bromide, which has a cream color. If it was chloride ions, it would be a white precipitate, and if it was iodide ions, we'd get a yellow precipitate. So this is looking like the anion is bromide, and then we can just test that when we added some chlorine, we got a displacement reaction happening here, and what was pushed out? Which halide ion has an orange color? Well, that will be the bromine ions. That will be the bromide in solution will be orange, or the bromine, I should say, in solution, not bromide. Yeah, so it's all pointing towards this being barium chloride. Barium, because we've got the white precipitate with the sulfuric acid, and then bromide because of our answers to test 2 and test 4. We can see that bromine was displaced by the chlorine because chlorine is more reactive in test 4. And so our unidentified compound is going to be barium, not chloride, barium bromide. Lovely jubbly. All right, let's move on to question 21. Again, we'll have to scroll up to look at the table, but first let's look at the question. What observation is expected in test 2 for solution S? So let's go up, and is it a yellow precipitate, white precipitate, effervescence, or no change at all? Well, let's go and check out test 2 solution S in the table and see if we can work it out. Okay. Well, it gave off a white precipitate, probably got barium in it as well. And then test 2 is really testing for the halide. Is it bromide, chloride, or iodide? Well, we can't work it out from that. We've got to go over to the displacement test, which is test 4, and that is going to give us the answer. Chlorine displaced a halide here because we've got a color change. What halide is going to give a dark brown solution, or what halogen? And you know the answer, it's going to be iodine. So if we did test 2 on iodide ions, what are we going to get? We know that the chlorine has displaced the iodide ions from the results of test 4. But if we did test 2 on iodide ions, we did the silver nitrate test, what are we going to get? We're going to get silver iodide. And what color are they? They're a yellow color. And so we're really looking for the answer that says we're expecting a yellow solid. Lovely. All right, guys, coming near the end of the exam now. Make sure you hit the like if you haven't already. If this has been useful, leave a comment. If you found something a bit annoying or not very useful, please also leave a comment. I'm trying to improve the videos. So we're looking at 22. Test 2, the mixture formed by solution S is filtered. Which substance is present in the filtrate? It's really hard to say what the correct answer is here because the exam board put an asterisk next to it and gave every single student this answer. And the reason is that they made a mistake in the question. They didn't necessarily say what the mistake is. So we could kind of try and guess at what the mistake is to try and work out what a correct answer could be. But who knows? So they said that in test 2, the mixture formed by solution S is filtered. Which substance is present in the filtrate? Some people think they mean which substance would be present on the filter paper. And if that was the case, it would be B, the silver iodide, because that's the solid yellow precipitate that got formed. So some people think that that was the answer they were going for, and they meant to say what substance is present on the filter paper, and that would have been silver iodide. Okay, but it could have also been a different version of that. They basically said the question was wrong, worded incorrectly, and gave every single student the mark, which doesn't really help anybody. Okay, let's look at question 23. And this could be the final question of the paper. It is the final question. What could be the identity of the compound in solution T? So let's check it out. Is it magnesium chloride, barium chloride, magnesium bromide, or barium bromide? So we need to look at all 4 tests and see if we can identify the positive metal ion and the halide ion. So when acid was added, no visible change. When the sulfate, so it's not barium. When they did the silver nitrate test, they got a white precipitate. That suggests chloride ions because we'll get silver chloride. When they added sodium hydroxide, we got a white precipitate. Now, there are actually 3 different metal ions, at least, that give a white precipitate with hydroxide ions. And that's magnesium, you've got aluminium and calcium. But obviously, you just choose the one that's there. Aluminium ions, they dissolve in an excess of sodium hydroxide and go colorless again. So this is going to be magnesium or calcium. However, I don't think calcium was one of the options. So we're really looking at magnesium. We've already identified the anion was chloride. And then we can see from test 4, when they added solution, there was no change. Well, there wouldn't be if you're adding chlorine solution to a compound of chlorine. There's not going to be a halogen displacement reaction there. So that makes sense that it's chloride ions. And it looks like it's magnesium because magnesium gives a white precipitate with sodium hydroxide. So we're going magnesium chloride for this final answer. And yeah, look, there is no aluminium chloride or calcium chloride. That would also give a white precipitate. Super, and that's the end of the test. Make sure you hit the like, subscribe, share, and whatever you do, leave a comment so I can improve.
You're still here? It's over.